Hello. Today we're going to go over titrations. So the next portion within chapter 17 is our titrations portion. So a titration itself is the addition of a strong acid with a known concentration to a specific amount of specific amount of base at a known concentration, or vice versa, strong base to a specific amount of acid with an unknown concentration. So here we have, with our strong acid, we have a known concentration. And our base has an unknown concentration. And we could switch it up. We can have the addition of a strong base. Again, still our known concentration. And with our acid, we'll have a specific amount, so we'll know exactly how much of our acid we have, but we won't know the concentration. Generally, what we're trying to get is that concentration of the unknown. So this is going to be a neutralization reaction. Or this will be a neutralization reaction if we have an acid-base titration. There are other types of titrations. We're only going to look at acid-base titrations today. So, it's a neutralization reaction. We are trying to neutralize the unknown with the known. So we keep adding until we get to a point where we reach neutralization. So we're trying to determine point of neutralization, because neutralization means concentration of H plus is equal to concentration of OH minus, right? So at this point, we know that our moles of acid are equal to our moles of base. And then from this information, we can determine our concentration of our unknown. Okay. We generally plot the data we get from this in a titration curve. So with a titration curve, you're going to be plotting volume of titrant. So this can be the strong acid or strong base with known concentration versus the pH of the analyte. This is going to be the unknown. Okay. Now, let's say we have an acid titrant and a base analyte. We're looking at the pH of the base analyte, so it's going to start up high, and then it's going to go down as we add in our titrant or our acid until we reach what's called an equivalence point. And this is when our OH minus equals our H plus. Okay. We can do it the other way. We can have a base titrant, acid analyte. So in that case, since we're looking at the pH of our analyte, we're going to start out low, and we're going to increase until we reach our equivalence point. Okay? Okay, so using our volume of titrant at equivalence, and our concentration of titrant, we can determine our moles of titrant to reach neutralization. So, therefore, since OH minus equals H plus, we can also calculate the moles of our analyte. So if we have a 1-to-1 mole ratio of H plus to OH minus, so if we have a dibasic base and a monoprotic acid, then our moles of acid will equal our moles of base. If we have a case where we have a dibasic base or a di or tri protic acid, then we will have to do some additional calculations. Okay, so generally we think about, with our types of titrations, we're going to have a strong titrated with strong, or a weak titrated with strong. So our analyte can be a strong acid, weak acid, strong base, or a weak base. Our titrant, on the other hand, must be either a strong base or strong acid. Okay? If we have a weak acid and a weak base, it will not be a titration, it will be an equilibrium process. In class, we'll go over the steps of how to determine pH along the way. There's several steps depending on where you are within your titration and what type of titration you're doing, whether it's strong-strong or strong-weak. So we'll go over all of that when we go to class. But some other things to note: your equivalence point will be different based on whether or not you have a strong or weak analyte. So if you have a strong analyte, your equivalence graph or plot, we take your volume of analyte versus your pH, sorry, not volume of analyte, volume of titrant added versus your pH of analyte. If you have, so you'll either have this occur, right? So we've looked at that one, and this pH will be 7. Let me just actually. So this pH of neutralization will be 7. Whether it is a base analyte or an acid analyte, they'll both be a pH of 7. Okay? If you have a weak analyte, you're going to have a weird kind of dip occur, an initial dip, and then a slow kind of decrease, and it'll look more like this, so it won't be a stark drop off. So your equivalence range will be a little bit smaller. And if you have a weak base, strong acid, this pH is going to be less than 7, so it'll be like 6 or something like that. And then if you have the opposite occur, you have a weak acid, something like that. That equivalence will be something more like 7. So, or sorry, 8, excuse me. So a weak base being titrated with a strong acid will have a neutralization that is lower than 7. Neutralization pH is lower than 7. This has to do with our acidity and basicity of the salts that we produce. And then a weak acid titrated with a strong base will have a basic neutralization point because we'll have a basic salt that's produced. And another thing I want to note, halfway between your equivalence point and your starting volume, so somewhere halfway between these 2 points, we have our pKa equaling pH. So whatever the volume that is halfway between our initial 0 volume and our equivalence point. So basically half your volume to equivalence. pH or pKa will equal pH, or rather in the case of the base, pKb will equal pOH. Okay? So again, we'll look at some examples of all of these, how to do these calculations. We'll be able to we want to, at the end of this, be able to calculate pHs all the way throughout our titration, whether we have a strong analyte or a weak analyte. Another thing we're going to be looking at in today's lecture is indicators, which basically have different colors at different pHs. So what an indicator can be used for is to show the equivalence point. So we'll be looking at indicators as well. There's a bunch of different kinds based on where your equivalence point is. So picking a good pH indicator will be able to give you a visual means of watching the reaction. We're also, in this lecture, going to be looking at what's called, so we're going to go away from titrations. We're going to look at what's called KSP. So KSP is basically what we would call the solubility product constant. So we've talked about in 1211 the fact that we have insoluble salts based on our solubility rules. However, they are not truly insoluble. There will be some amount that will dissolve, and our KSB will basically tell us how much. So if we have something like barium sulfate. Barium sulfate, when thrown into water, will be in equilibrium between its solid form and the dissolved ions. And this solubility is based on KSP. So KSP is going to be our ions themselves. So it's one of the easiest equilibrium expressions that we see, and this is not included because it is a solid. Okay. So we are going to look at calculating KSPs and looking at molar solubilities, determining molar solubilities of specific insoluble salts by using our KSP. We will look at different salts and calculate molar solubility and mass solubility, or take mass solubility or molar solubility and determine KSP. So we'll be able to go through there, but just to kind of give you a diagram of what we'll be looking at. So if we have mass solubility of a specific compound, so it's going to be in grams per liter, we can use our formula weight to determine our molar solubility. This will be in moles per liter. We can also use our empirical formula to determine our molar concentration of ions. And then, using our solubility equilibrium. This right here. We can determine our KSP. So KSP is related to our molar solubility, our concentration of ions, and our mass solubility, and we will be doing calculations with these in class. Okay, see you guys later today.